those are just a couple examples of doing a zero launch angle. Zero launch angle meaning the y component of the initial velocity is 0. Now, zero launch height, we're talking about, in this case, where an object starts and ends at the same height. So we're saying y naught equals y final. Keep in mind that there will be symmetry. In this case, our trajectory will be, and just like we talked about for free fall in one dimension, this trajectory is symmetric. So we'll be able to use that for some things. There's one more equation that we can use, only for zero launch height. You don't need it because you can get it from other equations, but it's helpful. So our equations for projectile motion, for our time-dependent equations, look like this. And in this special case, y naught equals y final. That means our vertical displacement is 0. Okay. So, based on that, if that's 0, then we can say 1/2 gt squared equals v naught y t. A factor of time cancels out. Now, we also need to remember how to find our initial velocities. So here's where our trig shows up again. The x component of initial velocity, if we have some initial velocity at an angle theta, remember the x component of that vector is going to be v naught cosine theta. The y component of that vector is going to be v naught sine theta. Right. So let's solve this for time. We get time is going to be 2 v naught sine theta over g. Take that, plug it in over here. We get delta x equals v naught times cosine theta times 2 v naught sine theta over t, or over g, sorry. And this gives us our range equation. We've got delta x equals v naught times v naught is v naught squared. 2 sine theta cosine theta, you may or may not remember, but that's a trigonometric identity. 2 sine theta cosine theta is equal to sine 2 theta. And then g remains g. So this is the range equation that we can use only for the case of zero launch height, where we start and end at the same height. Our other kinematic equations still apply. The range equation is notable because it is the only equation for which you will ever plug in just the magnitude of the velocity. Okay? Every other equation, you will always plug in an x component or a y component. And that's really what you're doing here, because remember we had a v naught cosine theta and a v naught sine theta, but because of the trig identity, what we wind up plugging in is just the magnitude. You should never plug just a magnitude into an x component equation or a y component equation. This is a common error that you should be aware of. So here are some example problems. Soccer ball is kicked from ground height at speed v at an angle above the horizontal. The ball travels horizontal distance d before hitting the ground. What horizontal distance would it travel in the air if it was instead kicked at the same angle at speed 2v? Well, we can consider this in terms of the range equation because we know the angle is the same and g, of course, is the same. So we can see that the horizontal distance traveled is going to be proportional to the initial velocity squared. So if we double the initial velocity, then 2v squared gives us a factor of 4, so the distance traveled is going to be 4d. Here's another problem. A football is thrown with initial velocity 23 meters per second at 35 degrees above the horizontal. It is caught at the same height from which it was thrown. What is the maximum height? Well, we know at maximum height, when we were talking about 1D, we said velocity is 0. And that's sort of true, but also sort of not. If an object isn't going straight up, then at maximum height, it still has a horizontal velocity. Okay? But the vertical component of the velocity is 0. So at maximum height, that means v final y is equal to 0. Remember, at maximum height, the velocity is not 0. The speed is not 0. At maximum height, side note, at max height, we only have the x component of velocity, which is constant. There is no acceleration in the x direction. So at any point in a projectile motion, the x component of the velocity will remain the same. It will be constant throughout. So at maximum height, the x component of the velocity is just what the x component always is, v naught cosine theta. The y component is 0. So the speed at maximum height is v naught cosine theta. So in this case, what is its maximum height? Well, we know v final y is 0. It's caught at the same height from which it was thrown. What is its maximum height? I guess I should say, what is its maximum height above the height from which it was thrown? Apologies, I should have included that in the question. Yeah, so max height, okay. Well, what do we know? What are we trying to find? What equation can we use? We can use our time independent equation. We have all the information we need to figure that out. Negative 9.8 times 2 gets us negative 19.6. We know v final y is 0. V naught y is not 23. V naught y is not 23. 23 is the magnitude of the initial velocity. To find the y component of the initial velocity, we need to take 23 sine 35. Don't forget that in every equation but the range equation, we are always plugging in a component, not a magnitude. And we get the max height is about 8.88 meters above where it was thrown from. Alright. At what time does the football reach a height of 2.1 meters above its original height? Well, time at which it reaches the height, that sounds like the time-dependent equation to me. And we can plug stuff in. Our delta y is 2.1. V naught y, again, is 23 sine 35. T minus g is 9.8 times half gets us 4.9. And we can punch it into our calculator. You can, straight in your graph, type in 23 sine 35, making sure we're in degree mode. If you're taking calc right now, you're probably in radian mode for calc, so make sure you're switching back and forth. That could be problematic if you don't. And at what point is it at a height of 2.1 meters? Calculate 0. And there are two answers. 0.170 seconds about. And calc 0 somewhere between 2 and 4. Guess 3. 2.52 seconds. Stop and think for a moment. What time does the football reach a height of 2.1 meters? Well, if it makes it to that height of 2.1, it's going to get there, and then it's going to go up and come back down and hit that height again. So two answers makes perfect sense in this case. So leave our two answers. That's just fine. How far away is the ball caught? Well, how far away? For this one, we can just go ahead and use the range equation that we derived. We plug in the magnitude of the velocity, which in this case is 23 squared sine of 2 theta. Theta is 35, so sine 70 over 9.8. So we get about 50.7 meters away. What is the ball's velocity as it is caught? Well, if you weren't thinking about this, you might, or if you were thinking about it in a different way, you might start going to equations and figuring out what to plug into. But instead of doing that, I'm going to remember, oh, it's thrown from this height, it's caught at the same height, projectile motion is symmetric. So its initial velocity is 23 meters per second at 35 degrees above the horizontal. So the ball's velocity as it is caught is 23 meters per second at 35 degrees below the horizontal, based on symmetry.